We'll continue today with discussing particle collisions and how we may use this four-vector notation to analyze them from a relativistic viewpoint. So just to mention briefly some of the key points that we discussed yesterday, perhaps the most important one was this possibility of having a conversion between kinetic energy and rest energy. That in general, the energy for a particle relativistically could be written the following way, which you can think of as a composition of a kinetic part and a rest energy, which is intrinsic to the particle. So it's an energy which the particle has even if it's not moving. And so since we know that energy can be converted between different forms, for instance from potential to kinetic energy, we can also have a conversion from kinetic to rest energy. And this has the profound implication that mass is not necessarily a conserved quantity in particle collisions. In fact, you can have a mass increase in particle collisions precisely due to the fact that kinetic energy may be converted to rest energy and hence enhancing the mass. So at the end of the lecture, we had just gotten started on a somewhat, well, what seems like a pretty complicated problem. This is the before situation. We have two particles colliding. And in the aftermath of this collision, we end up with, say, n particles, which all may have different masses. And so the seemingly pretty ambitious task that we set out on was to try to analyze this problem to see if we can say anything useful about it, even though we know nothing about the details of how these particles move or anything like that. All we know is what we start with, two masses m1 and m2, and what we end up with. So we had defined the total form momentum before the collision in the following way, just the sum of the two individual form momentum vectors. And after it was just the sum of the resulting particles. Now, we know two things about the form momentum, the total form momentum, which are crucial in order to analyze the problem. The first thing we know is that the form momentum is a conserved quantity. And I'm emphasizing here that it's a conserved quantity for a given inertial system. So the reason I want to underline this is that from its general expression, the conservation of the form momentum then implies that we have conservation of free momentum, just the usual momentum, and energy. However, this is only valid for a given inertial system, because if we change between different inertial systems, we can change the relative weight between the momentum and the energy. So for instance, in the center of mass system, the total momentum is 0, and hence we have some energy. But in another system, we may have a finite momentum, for instance in the lab system. And in that case, the energy will be different. So when I say P mu is conserved, that doesn't mean that P mu is the same in all inertial systems. It means that it's conserved in time for a given inertial system. And I'm emphasizing this to distinguish it from the next property. Namely, that P mu squared is an invariant in any inertial system. So that means that regardless of which inertial system we consider, P mu squared will be invariant. So it's important to keep in mind the difference here. Based on our previous experience, we've seen that working in the center of mass system is often very convenient because we lose completely the first 3 components of the form momentum. So we have the following situation for the center of mass system, where this term here vanishes. So P mu squared in the center of mass system is simply given as the negative of the energy available in the center of mass system squared divided on c squared. And what we did, the last thing I think we did yesterday was to define this as some equivalent mass, large M. And the motivation for introducing such a quantity is the known fact that if P mu is the form momentum of some particle with mass m, then P mu squared, it's given as minus m squared c squared. So we're just saying that the total form momentum squared is invariant, this we know, so we define this invariant in the following way. And so the question I pose to you as we closed yesterday was, is this equivalent mass equal to the sum of all the masses after the collision? Any ideas? So after the collision, we have produced a number of particles, but they are not necessarily at rest. They're all moving in general, because we need to conserve both energy and momentum from before the collision. So if we have a finite momentum here, then we should also have a finite momentum here. So they will have a kinetic energy, so the answer here is that this is not true in general. If p mu prime consists of the sum of a number of 4 vectors for all the particles after the collision, then this invariant, the equivalence mass, is not in general equal to the sum of all the masses of the particles, because this contains also contribution from their energy, the kinetic energy. So we're just introducing this as convenient notation based on this analogy here. So we've now evaluated this invariant in one system, the center of mass system, in which case we found it to be equal to this. Now, this is an invariant quantity, so we have to have the same before the collision. Now, this p mu is a bit more tractable to handle because it only involves 2 particles. So we might even be able to evaluate this expression explicitly. So we have this. Now, these terms here are easy to evaluate because they're just invariants as well. And since we're dealing with 1 particle each, they'll just be the mass squared. Yeah.
Are you now using mu as the annotation for that it's 4 vector, or as a summation index?
It's supposed to be.
Because if it's a summation index, then you would change it in the second parenthesis.
Right. Yeah. So I'm indicating here that it's supposed to be a summation index because I'm summing over. So this means P1 plus P2, etc. So I think it should be correct with equal indices here, since we're supposed to sum this factor here multiplied with this factor with equal indices. So this P mu is P1 mu plus P2 mu. And we want to make a sum here, so we get P11 You see what I mean? So I think it's correct with equal indices here. All right, so these first 2 terms are just invariants. And we write them down. like this. The second or the third term here, we can't simplify much yet because we don't know anything about the momentum and the energy. It depends on which reference system we choose to work in. So this is the general expression for P mu, and we know that should be equal to this. So let me rewrite this. In the following way. Now, in order to proceed and evaluate this expression, we now have to choose a specific inertial system to work in. So we want to make a contrast because we evaluated this expression here in the center of mass system. But since it's an invariant, we can also evaluate it in a different inertial system. And the payoff of doing so is that we can then compare the two expressions we find in each inertial system and set them equal to each other. So let's say I choose a reference system which I call the lab system, for the reason that we may have, for instance, one particle at rest to begin with, and the other particle is accelerated towards this particle so that they collide. So I'm just choosing a specific inertial system where the reaction looks like this. So it means that P2 is equal to 0. And that helps us here because then we can discard this term. So we have this. So it's looking a bit simpler now. We can make even one more statement, because if we know that the momentum of particle 2 is equal to 0, then we immediately know what its energy is. So what is the energy of particle 2 in this inertial system?
M2c².
Yes. So it only has a rest energy. So inserting that into here, we get we get this. So note here that I've rewritten this slightly because I now have m1 plus m2 squared, where I before had the sum of the squares. So this gives me an extra term here compared to the first line here, which I have to subtract here. So the product of this factor and this factor gives me precisely this extra term. Okay. We have then obtained the following equation. That the energy squared, as seen from the center of mass system, which is equal to this invariant quantity, namely the equivalent mass, is given as the sum of the masses of the particles initially, squared, multiplied with C4, plus this term here, where I have defined K1 as this term. So what is K1? Does it have any physical interpretation?
Looks like the kinetic energy.
Exactly. It's the total energy E1 of particle 1 minus its rest energy. So it's equal to its kinetic energy. So this makes it very clear that this equivalent mass is more than just the sum of the reagents in this collision. It also contains the contribution from a kinetic energy. So another way to look at this equation is to say the following. The available energy in the center of mass system depends on the initial kinetic energy like this. So roughly, this available energy goes as a square root of the kinetic energy. So where this is the kinetic energy of particle 1. Well, I should add that this is strictly speaking only the case if the kinetic energy is much larger than the rest energies. So we can neglect this term. So we see that the energy available in the center of mass system increases slowly with the kinetic energy of the incident particle. Okay, so this looks like a neat equation, but is it of any use? Can we use it for anything? Does it have any practical implication? And in fact, it does, because this allows us to define a very important concept known as the threshold energy. Now, this is a quantity which would be crucial to us if, say, we were experimentalists in the lab and we had set up our target, some object or particle here with a mass m2, and then we started shooting some other particles towards it, for instance, electrons. And then we wanted to ask ourselves, what is the minimum energy required that these particles, or electrons in our example, have to have in order for this reaction to work? So we started out with 2 particles, and then we ended up with n number of particles with different masses. So the question is, what is the minimum energy I have to give these electrons to make this reaction start? And this is the threshold energy. Like this. So there's a minimum energy required in order to enable this reaction. Okay, so let's now try to think, just qualitatively. What kind of physical situation would the threshold energy correspond to? If you were to put it into words, just to explain it. What kind of condition would you need to have in the case of a threshold energy? So take a minute to think about that.
The difference between rest energies after and before.
Mm. So how do you? So what about the kinetic energy in that case?
Well, it should be the difference
Mm.
between the rest energies after and before.
Right. So basically, we need sufficient kinetic energy in order to produce the new masses. But that's it. We don't want any excess energy compared to that. So in other words, the threshold energy is the energy required just to provide this mass difference. So it corresponds to the case where all the resulting particles, M3, M4, etc., are at rest in the central mass system. So they have no excess energy. We just provide just enough energy to produce them, and without giving them any excess kinetic energy. That would be the threshold energy. So we want no excess kinetic energy, just sufficient energy to provide this mass difference. And in this particular case, we can say that the equivalent mass is simply the sum of the resulting masses. Where R stands for reagent. So the equivalent mass, the invariant quantity obtained by squaring the form momentum after the collision, is just given as the sum of all the resulting particles, because they have no extra kinetic energy. Okay, so let's try to analyze this particular situation to see what the threshold energy will be, given that we know all the masses in the system. So we then have the following equation, where I've now just substituted this sum in the place of the equivalent mass, large M. And this is the kinetic energy of particle 1, assuming that particle 2 is at rest. So this will be the threshold kinetic energy, the minimum energy that particle 1 has to have in order to trigger this reaction. So So this is the expression for the threshold energy in the scenario where particle 2 is at rest and we shoot particle 1 towards it in order for it to produce all the resulting particles, M3, M4, etc. So we see here that K1 consists of precisely the total sum after the collision squared minus the total sum before the collision squared, and then divided on this term here.
Is it K1 over M1 C squared?
Yes, sorry. Now, we can actually rewrite this equation in terms of a new quantity, which is used to characterize this reaction. We can characterize the reaction by means of the added mass that it produces. So we define the quantity Q as m after minus m before, so it's the generated mass. And by introducing this quantity, we can rewrite this expression by noting that the denominator here may be rewritten like this. So we get the following. So the threshold energy of this reaction may be expressed via the Q value, which is defined as the generated mass, in the following way. So we see then that even though we started out with a situation which looked a bit complicated, we had two particles and we ended up with n particles, and we knew nothing about the details of the collision, but we were still able to, via this analysis with the four momentum vectors, we were still able to say something sensible about which condition that needed to be fulfilled in order for this reaction to work. Namely, we identified the following equation here. So let's have a look at a couple of examples of how we can use this. So I'll start out with two pretty easy examples just to illustrate a principle. We'll consider first the production of an antiproton, which can be done in the following way, where this large n is the constituent of a nucleus, so it's either a neutron or a proton. So P over bar denotes the antiproton. So let's have a look at the masses involved here. We have well, the masses of the proton and the proton are the same, and they're roughly the same as the mass of the neutron. So let's just define the mass of all the involved particles as m, since they're almost the same. And numerically, it's given by 938 mega electron volts per c squared. So this notation is often used in particle physics. This has dimension mass. Energy divided on velocity squared has dimension mass. So this is often more convenient than writing 10 to the minus, 25, something like that, kilograms. So particle physicists often use this kind of notation. Okay, so what's the Q value for this reaction?
Two.
2m. Exactly. It's just 4m minus 2m. So we may then just plug it into our formula here to find what is the threshold energy. Say we accelerate this proton to hit this nucleon. What is the threshold energy of this proton in order to enable this reaction? Okay, so Q is 2m. So we get this. So in other words, the incoming proton needs to have a kinetic energy equal to 6 rest masses or 5.5 GeV in order for this reaction to take place. And this is useful information because say we want to produce this reaction in the laboratory, well then we need to know how large voltage, for instance, we need to accelerate the proton, or similarly, whatever mean you use to obtain the situation. Now we know exactly how much energy we need to provide the proton to trigger this reaction. So we'll have a look at a couple of more examples after the break.